Coming up on Conversations on Bionics and Pain.
Elliott and I have had an interesting friendly debate about is the hardware the limiting factor or is the control the limiting factor? And that's, we've been reluctant to talk about it too much at scientific conferences, but maybe a podcast is a good place to bring that up.
Please.
So I would say that I'm frustrated sometimes when I hear that, control is the limiting factor. I don't think that's the case at the moment. I think hardware is as much a limiting factor as the control. And so there are limitations in what we know and understand about how to control these devices, but the hardware has a long way to go before we're able to really try and see how well some of our control approaches work. And so I'm kind of off the control is the limiting factor to it's a limiting factor. Mm-hmm. And so maybe Elliott's came around to my way of thinking because I phrased it a lot more gently than I would phrase it over a beer or three.
Welcome to Conversations on Bionics and Pain. I'm Dr. Max Ortiz-Catalan. I'm the director of the Center for Bionics and Pain Research, which is a multidisciplinary engineering and medical collaboration between Chalmers University of Technology, Sahlgrenska University Hospital, and the University of Gothenburg in Sweden. This podcast is about the development of medical and engineering technologies to restore human function and alleviate pain, but it's also about the people dedicating their lives to this development and their stories. You are now listening to the first episode dedicated to a scientific article that is titled Design and Clinical Implementation of an Open Source Bionic Leg. This was published in Nature Biomedical Engineering in October 2020, and it was a collaboration between two research groups, the first one led by Professor Levi Hargrove at the Sherly Ryan AbilityLab in Chicago, and the second one by Professor Elliott Rouse at the University of Michigan. We had a relatively long chat where we talked about the need of having an open source device that allows for research. We discussed the limitation of prosthetic legs at present, hardware, control, sensor feedback, and the potential directions in which research could move forward. We also touched upon how one can identify bad ideas and discuss a few advices for students and young researchers. So without further ado, here is the conversation. Will you mind introducing yourselves and how you end up where you are today?
Maybe I can start. So I'm Elliott Rouse. I'm an assistant professor at the University of Michigan in the Department of Mechanical Engineering and the Robotics Institute. There I direct the neurobionics lab where we study how the nervous system regulates the mechanics of locomotion. So concepts like joint mechanical impedance and its role in stability and system dynamics of gait. And we also develop wearable robotic systems like exoskeletons and robotic prostheses, things like our open source robotic leg, which we'll talk about today in this chat. Kind of my path was a little bit different. I started out in professional auto racing and then really became kind of compelled by, I wanted my work to kind of have an impact on people's lives, in particular people with disabilities. So that kind of led me to return to grad school and work with Levi and Dr. Kaiken and eventually pursue academia as a career. So now I've been a professor for about 6 years.
Nice. So you graduated, work a little bit, realized that work wasn't exactly for you, and then went back to school to pursue a PhD.
Yeah, I actually worked kind of full-time and went to undergrad full-time. So I kind of did those things in parallel. But I sort of, at that time, wasn't ever expecting to leave auto racing. So it was a sort of an amazing experience, and I thought this is sort of what I'll do for the rest of my life. And then I sort of decided I had to leave.
Right. Yeah, prosthetic seems to be a field that appeals to people, and then you maybe start just wanting to try a little bit and then end up full time. Mm-hmm. All right, thanks.
Yeah, my name is Levi Hargrove. I'm the director of the Regenstein Center for Bionic Medicine at the Sherly Ryan AbilityLab in Chicago, and the Sherly Ryan AbilityLab is formerly the Rehabilitation Institute of Chicago, and I'm also an associate professor at Northwestern University. I've been in the field for nearly 20 years now. I started off doing research related to upper limb prosthetics in around 2002. And then I had a good opportunity to move to Chicago when Todd Kuiken was developing his targeted muscle reinnervation program down here. And then as kind of joined the group, we started working with prosthetic legs in addition to arms, and have since kind of grown that program over the past decade or so. So we have a pretty large team. We do look after all levels of amputation, arms, legs, and other conditions as well, spinal cord injury, some exoskeleton research similar to Elliott. And we just kind of see what we can do to translate things as soon as possible and do a lot of patient testing, maybe not as much hardcore mechanical engineering or mechatronics engineering as some of the mechanical engineering departments at universities, but we really try to get technology on patients to try as soon as possible.
The translational research part of the development of the devices.
Yeah, we do both, but we focus on the translational part for sure.
Right, good, thanks. You published an article in Nature Biomedical Engineering in October 2020, and it is about an open source leg prosthesis. And I guess the obvious question will be, why do you think we needed an open source leg prosthesis?
So the reason, this originally kind of came from discussions that Levi and I had a long time ago. And particularly there was kind of a workshop at a conference maybe in like 2012 or something, where controls researchers in the field of prosthetics were sort of discussing the fact that they didn't have a hardware platform, and everyone was sort of forced to develop their own hardware solutions. And they were sort of noting to those of us that develop these systems that there was this need to kind of help develop a community and a common hardware platform that would help us kind of address the control barriers kind of more efficiently and more quickly. And that kind of planted the seed. And then I'd say like over the next few years, we just kind of kept talking about it. And then maybe around 2014 or 2015, we sort of kicked it off, started submitting grants, started some preliminary work. And we developed it from there, got some grants from the NSF, which was really helpful. And we developed the system, started with a knee, and then transitioned to developing a knee ankle system. And the community support has been amazing. So researchers from all over the world have sort of begun using the system, and people have contacted me, sort of volunteers wanting to get involved, general public kind of interested in learning about it or doing sort of different aspects of volunteer work, which has been like pretty exciting. It's kind of a different, I wasn't imagining that kind of part of the way that we would do academic research would include sort of a crowd-sourced version of some of the work just by people who are excited and interested and skilled. So that's been really, really, really cool. But I'd say it really came from a gap in the field that was noted by the researchers that were intended to benefit from this technology.
Yeah, we started doing work related to kind of high-level control, what the person is trying to tell the prosthetic to do, in around 2008. And we partnered with some excellent Michael Goldfarb at Vanderbilt and Hugh Hare at MIT, and they had excellent hardware. It was really top-notch. And so our goal at that time was to only work on the control system of the device and not develop any sort of new device at all. And kind of as we continued to push the field forward and do our line of work, we did see a need that, we needed a device that we had full knowledge on, could repair easily, quickly, make a second version if we needed to. And so, we just didn't, as good as our collaborators were, and they were excellent, that cost time and money for them to continuously build us new devices and repair them. And so when we had this opportunity, we thought, well, let's do something so that other people don't have to reinvent the wheel that we're inventing now. And there are a lot of reasons to not make things open source, and I fully understand why you wouldn't do that. And we have devices that we're working on here that we protect intellectual property on, et cetera. But the benefits of doing this particular project kind of, it's for the research community, and it was a positive thing. So we're fully supportive of it.
Right. So it came from a need. People realized there was a need because there is no commercially available prostheses that have both an ankle and a knee that are power that you could just buy and use.
Buy and use and understand fully.
Yeah, and you couldn't. The ones that if you could buy one, you can't program its controller. So that was like a key limitation. And I think like the challenges that Levi's mentioning are like the same challenges that Bobby Gregg is facing and Harbu Geyer and other researchers kind of around the world and around the country are facing. So that story like kept coming up that we need a hardware system that is relatively simple and easy to repair and low cost. And we kind of took up that challenge.
So the development of the leg started when you were working in the same institution.
So we were both principal investigators at the same institution, and we were just kind of collaborating. Elliott was doing some mechanical work, and we were doing some different control work. And we thought that it would be a good opportunity for us to put our two labs together and make something.
I noticed you using the same actuator for both joints, and I guess that was a design consideration you wanted to have.
Yeah, that's right. Yeah, like the actuator is actually like a lot of thought went into what actuator we used. Some of the kind of key decision points were that we wanted to use actuators that were developed by the drone industry, so these large diameter motors that have particularly high torque density, and that opened some doors for us in terms of design. So if we have more torque from the motor, we can lower the transmission ratio. If we can lower the transmission ratio, we have new options on the table for what the transmission can be comprised of. And we ended up going with something like belt drive transmissions, which are low cost and low lead time and quiet and efficient. So that kind of started with a selection of an actuator. And then kind of secondly, kind of in line with that, we worked with Luke Mooney at a company called Defy, who had developed a brushless motor drive and API, so communication protocol that let us command these motors. And at that time, these motors have many pole pairs that many brushless motor drives were not able to efficiently commutate. So at that time, there weren't a lot of options to actually control them. So this company, Defy, led by Luke Mooney and JF Duval, had created this brushless motor drive, and we ended up using that technology in the open source leg as kind of an off-the-shelf commercial product. And the technology in this brushless drive stems from some work that was done with Hugh Harris Group at MIT that was an open source brushless motor drive. So it kind of started, we were originally intending the drive to be open source, but the sophistication of kind of implementation of the open source version of that we thought became too high to expect researchers to just use that or do it. So instead we kind of transitioned to this off the shelf version from Defy, and it's worked very well.
I would also say that, using the same actuator, modularity was something that we wanted. So this is a knee ankle powered device, but we also thought, well, if someone only wanted to use a knee or only wanted to use an ankle, they would be able to do that without having to learn two different technology stacks.
Yeah, that's right. I mean, that adds to the convenience and the kind of ease of use, is that the same controller APIs and controller programs can be used to control the knee or the ankle or both. Yeah, that's a great point.
I guess people are used to having open source software where everything you need is there. But in hardware, it's a bit different because some things you might need to buy from some suppliers. So I'm guessing that you were also making those considerations to make sure that the stuff that will be needed to build the leg will be also available for people, and not only in the United States, but around the world.
Yeah. We actually spent a lot of time thinking about this. We tried to use as few vendors as possible. So that was one consideration. So not have all the parts come from kind of many different suppliers, which would increase the burden on kind of purchasing the system. And then we also tried to have the machine components leverage as much stock material as possible. So for example, the timing belt pulleys are stock pulleys. You can buy them and kind of chop them or post machine them and use them. But as it turned out, we kind of designed with that in mind. But when we ended up having a machine, most of the machining is done by a company we work with in China called Star Rapid. And they just machined it all from scratch anyway. So they ended up not actually using the stock material, but it was a design consideration that we had from the start, was to kind of minimize the number of suppliers and the kind of machining burden required to develop the system.
What about user requirements?
User from the perspective of the researcher or the engineer assembling?
The researcher, the assembly, but also the patient who's going to be, using it. Because the purpose of the leg, I understand that is for research. But I suppose that you also intend patients to use it eventually, or is that out of the scope?
So Ellie and I may have different opinions on this, but I don't envision this as being a device that someone would use at home as part of their daily use regimen. So I think that they could go out in the community under the supervision of a researcher. They might be able to use it for an afternoon or a couple days, but not something that they could use kind of every day. And some of the design choices that we made with that in mind. I think the real sweet spot is going to be the research team who can get kind of out of the lab with like tethered controllers and power supplies plugging into the leg, maybe get outside onto their university campus or their hospital environment, maybe go out into the community a little bit. And that's a big step over what would be available for many of the research devices right now. So it's possible in the future, as we refine this, we may leverage some of the key concepts into a translatable daily use device, but I don't think the entire device itself.
Yeah, I agree. I think I would say the same thing. We designed the system to be for use in the academic community, and that kind of factored into a number of the decisions that were made. So while maybe it has potential to be a commercial product that ends up being like used by kind of people kind of in daily use, that would be exciting, but that certainly wasn't the intention. And if we were designing it for that situation, I think we would make some decisions that were different. Like, for example, the knee is designed to have a kind of robotics component called a series elastic actuator incorporated into the knee joint, which allows for high fidelity torque control, energy storage and return, and some other things, which is really that serves control researchers as opposed to potentially like end users. So if we're designing for end users only, I think maybe we may not have designed it that way.
I find this interesting because that particular design consideration, if you have that capability for the engineers working on the control, and then they develop something that is great with that hardware, then they won't be able to implement it in a leg that doesn't have it. Or will that be able to translate to a leg that doesn't have that kind of capabilities?
So I think if you demonstrate the improved, and this is one of the primary reasons we developed the leg, was so that we could compare approaches and demonstrate like dramatic or even small improvements over state of the art. And from my experience working with companies if you can demonstrate something that's clearly better, you have an excellent opportunity to reach out to them to get that feature incorporated into a manufacturable commercial device. And so that would be my view on it, is if your approach, the series elastic element was fundamental to your control approach, and your control approach outperformed the comparison condition by a clinically significant margin, I think that the leg manufacturers would be very receptive to modifying or building a new device that incorporated this.
Yeah.
Okay, so if I make an analogy with the upper limbs, will be like most hands use 1 degree of freedom, and then you build a research hand that has individual ectotic fingers, and then you show that the function is a lot higher, then that will put the pressure on the manufacturers of the single degree of freedom hand to produce hands with individually actuated fingers. So you're really making this platform as a Ferrari, like a top-notch device to develop sophisticated stuff that once you can show the clinical benefit of, can tell manufacturers or established companies, this is the kind of stuff you want to go because patients have benefits on the technology.
Exactly.
Yeah, I think that's right. And
that's a great analogy.
And like for specifically the series elastic element, the knee joint, for example, can be used both with and without the series elastic component. So it lets researchers sort of explore this idea of, is including series elasticity sort of worth the trade-off, because it adds mass and complexity and robustness challenges. So if it turns out that what we learned from studying control using the open source leg is that the series elastic actuator is kind of worth this trade-off, then that would be information that could be passed down to manufacturers. But I think, this gets to the original idea of kind of why this is a potentially valuable platform.
Right. Yeah, and I think this is an important point because, when we try to develop the new technologies and we present this stuff in some conferences, we're often criticized by the practitioners saying like, well, it's all very nice, but, I can't use it with my patients. And sometimes, like in this case, the intention is to push the edge on what's possible. So then you can drag with you the manufacturers that will make the commercially available device possible.
Mm-hmm.
And I think that message is good to be clear so people don't have the expectations, oh, well, this is an open source leg. I want to build it and start using it with my patients. It wasn't designed with that purpose in mind.
Yeah, that's absolutely right. We would encourage people to use it to push their research forward. And it is great to get feedback from the patients who are using it, just maybe not as part of their everyday lives just yet.
Yeah, because in the article you report, you had it used by 3 patients, I believe, who have used power prosthesis in the past.
So in the article, I think we reported 3 or 4, but we have had, I think, nearly 20 or 30 use the device,
okay,
and who have used other power devices, since the time that we wrote the article and it did the full experimental protocol that we reported on. But we've had, I think, at least 20 users use this particular device, and they all have differing feedback depending on the experiment that we did on any given day.
Depending on the controller that you were testing, I guess.
The controller that we were testing, this is a great device. It's a newer device, so we're always looking to make enhancements. So some of the early users didn't have the opportunity for some of the enhancements that we've made. Next would be stronger materials, different, even things like we're learning in the socket. This isn't directly related to the device, but learning how to suspend the device better to make it more comfortable, just because it is a bit heavier than their C-leg, for example, or their Rayo knee or whatever they're using. And so some of the early users didn't have the opportunity to use as comfortable a fitting socket. We've learned as we've went along the way. And so all of those other issues impact their opinion of any new technology.
Do you think that when you're using a more sophisticated leg, it's even more important to have a perfectly fitting socket because of the...
My opinion is it depends on what you're asking when you're doing the experiment. So if, for example, if we are demonstrating someone can walk up stairs with a reciprocal or step over step gait, they need to have a comfortable enough socket to tolerate the forces and torques that are on the residual limb. But if we're only doing an hour-long experiment, we may not need to worry so much about a pressure sore formation after 10,000 steps, for example. And so we may choose a slightly different socket. We also might want instrumentation like pressure sensors inside of the socket or EMG sensors, for example. And so that will impact socket fit. And so that's again, just a different challenge of doing lots of experiments to evaluate lots of different things at the moment. And it's kind of not what was in the paper, which was just straight up demonstrating ambulation across several activities.
Mm-hmm.
So I guess something that is closer to my own work, what do you think is the need of having neural commands? Because presumably with this hardware, you can take better advantage of using signals coming from the patient, or you think that now because you have a leg that has more instrumentation than conventional ones, you won't need neural drive?
That's a real interesting question. I would say that we have the opportunity to make legs much more functional than they are just using sensors like cameras, load cells, inertial sensors. However, we haven't been able to approach the peak of what would be possible because we don't have a good enough neural interface yet. And so I would say that, we can make an important step in control and performance using non-neural interfaces. And then I think you'll see another step, which may be even bigger, maybe not, but it may be even bigger from that level to approaching something that's, I won't call it normal ambulation, but, ambulation that allows you to do spontaneous activities and you get outside of kind of cyclical activities like only walking or going up and down stairs, like maybe mountain climbing, all sorts of different activities that we haven't even thought about yet. We'll have to wait and see on that. Elliott probably has other thoughts on it as well.
I personally would love to have like some neural information to help our control systems, but at this time, the like uncertainty is too large. We can't get a strong enough control signal to actually use it in our controllers. The reliability of the onboard mechanical sensors is so much greater. So that kind of dominates the control decisions at the moment. I'm definitely hopeful that in the future we'll gain access to some neural information. I think that will change the game. Like that's, I think, partly what we're waiting for is something. I mean, we can get, there's only so high I think we can get with the onboard mechanical sensors. But given that the leg is supporting the body, there's a lot of risk associated with fall or injury potential. Right now, we have to go with the sensors that provide very strong signal to noise. So hopefully, eventually, we'll able to get neural signals that kind of fit that description. But currently, I'm not sure we're there yet.
I mean, we're working on it, but it's taking time.
I think that in a short-term lab environment, so if you want to spend 2 hours setting things up in a real precise way, we've been able to demonstrate some benefit in using neural signals. And so it's about 2 hours of setup and 1 hour of troubleshooting and 1 hour of experimentation. And when you do it carefully like that, you do see a benefit, and there is a clear benefit. However, that's not clinically deployable, in the opinion of our clinicians, and they're definitely correct. And so as we can improve the robustness and have access to even more neural signals, then I think we'll even be able to push the envelope further. So I wouldn't say that we haven't shown benefit yet. I would just say that the benefit hasn't outweighed the kludginess of the setup.
Right. Yeah, but I guess that's our job, kind of, to push the...
That's your job number one. I've read about this osseointegrated neuroprosthesis that would be tremendously helpful in what we're doing.
Yeah, we're really looking forward to start testing. And of course, one of the reasons for me to get interested on your development, and we, as you know, we're planning to build one in our lab, is to do this testing because we collaborate with Azocar and we collaborate with Autobot and so on, but Azocar has a power knee, Autobot has a power ankle. And then if we want to put those two together, we need to get them to collaborate, which, I mean, they're great guys, but they're still independent companies. So there are some conflict of interest that hopefully we can work out. So we talk a little bit about the challenges. We mentioned the connection with the person is important. So the way it's fitted to the patient, and then potentially neural signals could improve leg prosthesis. What other challenges do you see for lower limb prosthesis? You have 2 actuators. Do you think we need more degrees of freedom?
Yeah, I think that's a great question. Personally, kind of at this time in the field, I would not recommend doing more degrees of freedom. I mean, it's interesting from a research perspective and a mechanical design perspective. There's definitely good work being done and good things to learn. But in terms of if we're talking about a potentially like clinically deployable system, as we mentioned kind of before in this talk, like adding other degrees of freedom increases complexity, it increases mass, it increases controller burden, which is already a very challenging problem. So at this time, I'm not sure I think that adding another degree of freedom kind of is worth the offset or trade-offs that occur. But I'd be interested to hear Levi's take.
Yeah, so I agree with you. I understand what you're saying. However, I do think it depends on if you are developing for above knee or below knee amputees. And so if you have a below knee amputation, perhaps you do want 2 degrees of freedom. Let's put it this way, whether it's active or not, you might want to control the medial lateral compliance. Whether it means a motor or not, it's different. So I think in terms of active degrees of freedom, I agree with Elliott, but in terms of allowing control over other degrees of freedom without an actuator, I think that there's questions to be answered there.
Yeah, I think it is true that a passive degree of freedom could be beneficial. And I think some prosthetic feet are sort of bisected through the midline to kind of add that passive degree of freedom. And something like that could eventually be implemented on the open source leg if it turns out that that's helpful. But I agree. There is some some room, I think, for a passive degree of freedom that might add benefit. But in some cases, some of that passive degree of freedom is taken up by relative displacements between the prosthesis, foot shell and shoe, right, for example.
And in the case of non-osteo-integrated interfaces, there's a lot of compliance between the socket and the residual limb as well. Just it's not suspended nearly as well as what you would have access to using the OPRA system, for example.
Attachment, right?
Yeah, exactly.
Elliott and I have had an interesting friendly debate about is the hardware the limiting factor or is the control the limiting factor? And that's, we've been reluctant to talk about it too much at scientific conferences, but maybe a podcast is a good place to bring that up.
Please.
So I would say that I'm frustrated sometimes when I hear that, control is the limiting factor. I don't think that's the case at the moment. I think hardware is as much a limiting factor as the control. And so there are limitations in what we know and understand about how to control these devices, but the hardware has a long way to go before we're able to really try and see how well some of our control approaches work. And so I'm kind of off the control is the limiting factor to it's a limiting factor. And so maybe Elliott's came around to my way of thinking because I phrased it a lot more gently than I would phrase it over a beer or three.
I would say there are limitations on both sides. So I'm sort of with you that hardware is a challenge, no doubt. In my mind, the difference is like whether the challenges stem from fundamental limitations of kind of what we know or the technology itself, or whether they stem from sort of practical issues of time and money, for example. So in my mind, like the hardware design, like we actually, as like humans, we kind of know how to design very sophisticated mechanical systems. We sort of like, over the last several hundred years, we've done really well with designing machines. And a 2 degree of freedom robotic leg is sort of no different. It just requires some sort of modifications based on making it lightweight and high performance. But then again, if you have a single lab developing it on government funds, that's not usually, it's some resources, but it's not maybe the resources needed to develop a system that's as robust as what would potentially be needed for long-term use in the field. So we've maybe started on that with the open source leg, and I think there's more revisions that need to be done and more refinements that need to be done. In my mind, on the controller side, it feels different because it seems like a very large challenge that has fundamental issues. Are we even able to know from the available data that we have, what is someone doing? What's the appropriate torque to provide? How do we recover from something we've never seen before? What's a stumble look like or a stumble recovery? So things that I think there are kind of fundamental issues about the science and engineering that are maybe present in sort of controller research that are less present in sort of other areas. And I don't think of that as a bad thing. I think of that as kind of the state that's like the leading edge. So we're up against the leading edge and we're solving challenges kind of as fast as we can. And it seems to be it's a very challenging problem. Control a high degree of freedom or a system with many state variables with very little information that has to get it right basically all the time. So that's a very, very, very challenging problem in my mind. But not to discount what you're saying also, Levi, like, hardware, both sides are very challenging. So I'm kind of with you there.
I just find it frustrating that it's harder to get research funding to develop a better actuator for the prosthetic, for a bionic leg, for example. So, I could write a grant because Elliott is right. There's fundamental hypothesis-driven questions related to the control that we just don't know, and we do need to study it and figure them out. However, it seems to be, at least for the grants that I'm familiar with writing, it's more difficult to say what, the limiting factor at this point is just giving me $2 million to make this device more robust so that I can do $1 million study to answer this other question. Right. And so that's, I I don't know how to address that. I think that's just an ongoing challenge. And but I do think that, the open source leg is a great start, especially because we can repair if something goes wrong. It's designed so that if something does break, we know what the first thing to check is, right? So you can do maintenance on it, preventive maintenance. You can that's what we should be doing. That being said, I think that if we had a large opportunity for a large pool of funding and a good commitment from, say, Elliott's group, it wouldn't be our group, but it would be Elliott's group or some other top-notch mechanical design group, to say, what we really need is you to take 2 kilograms out of this and make the battery last X hours longer. And I think that would be a very expensive proposition that's just hard to get funded. Thank goodness for the National Science Foundation who did fund this. But I think there's easily another $2 to $3 million that could go into this device that would open up opportunities for me to try new control approaches.
Yeah, I think that's right on.
Something that I often try to explain when people are just starting the field or patients is that there are different factors when working with a prosthetic limb. And I normally talk about 4. So the hardware, the control, the sensor feedback, and the attachment. And there are limitations in all of them. And sometimes, one, the smallest or the biggest bottleneck, depending on how you picture it. But I have the feeling that in upper limbs is certainly the control that is the limiting factor, and sensor feedback, which is absent. For lower limbs, it's harder to judge it because exactly what you said. There are some fundamental questions that requires hardware to be answered, which I think brings to me home the purpose of your paper and the importance of it. Because without this kind of hardware, is almost impossible to answer those questions. And then in this case, it seems like you need to push the boundaries of both the control and hardware more or less kind of like together to be able to answer the questions.
That's true. And I would add a 5th pillar, if you would, and it's especially important for lower limb, which is let's call it safety and therapy or instruction on how to use the device, because you can't even get up on a device unless you have either a therapist or a harness system or some instruction on how to use it. So yeah, you could put a prosthetic arm on with appropriate mechanical constraints, and you don't have to learn to walk with it. You need some instruction on how to use it, and that's very important, the occupational therapy. On the leg device, you actually need hardware to do the type of work that we're trying to do, right? So you can't do VR ambulation, at least not at the moment, although the emulators that Steve Collins and Humatech are designing are a good step in that direction. But generally speaking, you need actual hardware and instruction on how to use the hardware to even get started in this field where we're targeting the open source leg. Would you agree with that, Elliott?
Yeah, I think that's right. And I just kind of want to jump off of one thing you said, Max, which is like the sensory feedback part. So like the sensory feedback part is I think also like really important. And some people are starting to explore that in the lower extremity, but we haven't gotten very far yet. And I think that's a big open question. And I know Hugh Herr and Tyler Kleitz and Paul Soderna and others are kind of looking at kind of different options there. But I think that's still a huge open question that could have some transformative impacts on lower extremity robotic prosthesis use. But the field is, I think, further behind upper limb kind of as usual.
Yeah.
And I would echo that would even be important for non-motorized devices as well.
Yeah.
We see patients walking up and down the stairs. If they're above knee, they have no idea where their foot is, for example. Yeah. And so it makes it difficult to place your foot appropriately on the step. Mm-hmm. And so that's just one example of the challenges.
Yeah, because you can improve any of those parts, right? You can improve the hardware, you can improve the control, the sensor feedback, the attachment, socket to os integration, and they will all contribute to a certain degree to the improvement of function. And I guess something that I find difficult for us as researchers, it's to set the priorities based on the patient's needs rather than the things we find cool or we can get funding for. right? Because I will personally put sensory feedback with the lowest priority. So I will say, control is more important than sensory feedback. But I'm not a person that started my career on sensory feedback. So the people that started their career on sensory feedback will probably disagree. But there is contributions to be made in all these fields. And I guess this takes me to my next question. For students or people, thinking to enter in this field, where would you say will be the areas where there is, work to do, or where you would like to see people working?
Mm-hmm. Yeah, so I actually get this question a decent amount of time through students at Michigan. And the kind of some of the things I tell them are the kind of rehab wearable robotics space is a little bit different than a lot of other industries in the sense that the markets are generally small kind of at this time, which means the R&D departments in industry are sort of also like relatively small. So that means there's not a lot of jobs kind of in the industrial R&D world. The teams are small. And most of the kind of work, I'd say, the innovative work or kind of work kind of pushing the limits is done in academia, funded by the government. So that means like if a student would like to get into this field, a good place for them to start is an academic research lab. So getting involved, either when they're an undergrad student or a graduate student or a volunteer. I had, with the open source leg project, if you go to the website, there's, a student from India just contacted me, created a gazebo ROS simulation of the open source leg, and we posted it, and he's got a whole tutorial on it. And that was just, somebody who wanted to get involved, kind of did their homework, and now they're part of the project.
Contributions.
So, yeah. So I think the wearable robotics world is getting bigger, especially with exoskeletons kind of becoming kind of more in focus. But it's a little bit of a different kind of vocational landscape. And I typically encourage students to get involved in an academic research lab, even just on a volunteer basis, just to kind of get a feel for what it's like and see if they really want to go into this field.
Right.
I guess for me, I don't want to become an old curmudgeon, and so a lot of times someone will say to me, "Well, they tried that back in 1990 and it didn't work, so the idea is no good." And like a lot of things have changed since 1990, and you get the one of the examples are kind of the automatic grasp feedback for upper limbs, for example. It's like, well, people just turn it off, and I'm like, well, that maybe the idea was ahead of its time. And so when I talk with students, I really say you should review everything critically, everything that I've written in the past, everything that anyone's written in the past, critically, and then question if it still holds true or not. And so you don't really, you have to do it respectfully, of course, but you should be a critic of your own work and everyone else's work. And so I think that whenever I hear an idea that I don't necessarily immediately agree with, because I've read something in the past, I just kind of have to take a step back, and I encourage students to do the same thing. So often I'll ask the students what they're interested in, and if they have an idea that they want to pursue, because quite often they're pretty clever and they have a different angle coming from outside of the field that I haven't been pigeonholed in over the last 15 years or heard someone. And so that's one way I approach it. Scientifically, I'm interested right now in body area networks. So like connected sensing, cameras. For years, we only considered a sensor as long as it was attached to the device or the person. I don't think that that's the right thinking anymore, because technology has developed to a point where you could easily instrument the non-affected side. And again, that's an example of something that I would, just like the old OSER required an orthotic in the sound side in order for it to work properly. The old power knee, sorry. And it's like, well, that wasn't a great idea maybe in 2000, where it was perhaps kludgy, but now that's a time and money problem. And if that improves control, that would be an opportunity worth pursuing. So any sort of connected sensing, environmental awareness, et cetera, that's kind of where we're interested scientifically. And there's a lot of work to be done there.
Yeah, I think that's a great point. And And especially as sensing starts to become more integrated into clothing, like the whole sensing game is changing. And I think it's right to think like, okay, the conclusions maybe we drew 10, 15, 20 years ago aren't necessarily the same answers anymore. And I think that's a great thing to remind the field. Now it's not so hard to get sensors and get data, get information about location, get information about environment, things that you would never have had access to back then.
So now I'm going to take this conversation to maybe a more uncomfortable place, but also more interesting one, because I agree. It is true that because it didn't work in the past doesn't necessarily mean that it's not going to work now because technology is better. But everything is a trade-off, and they're also bad ideas. Right. I mean, and there's a lot of subjectivity in what is a bad idea. But the way I see it is why will I care if somebody's working on a bad idea if it's not me? And the reason why I will care will be that we have limited amount of resources. So we're a few people, there are limited amount of grants, and I would like to see the resources available to use in the best possible way. Now, myself or you or nobody can really say what is the best thing. But there are some things that are more likely to create a breakthrough than others. So my next question will be, how do you do to identify bad ideas and to kill ideas that you thought were good? And sometimes even your students might come with an idea that is maybe not great. And then you are in between motivating them to pursue it because, they came up with it. Or also, if you are interested on their career, I will say to some of my students, like, look, it's not going to be a game changer. So therefore, I will suggest that you focus on something that will have a bigger impact. I might be wrong, but I have a little bit more experience to say that. So what do you think about that?
I can
Well, I've certainly had my share of bad ideas and continue to. The question I ask myself is, there's good ideas that people tell you are bad, right? So it's actually a good idea, but people just say it's a bad idea, it's a bad idea. And sometimes you need the perseverance to just power through it. And then there's bad ideas that people tell you are bad. And so I think that whenever I guess for me, it's evaluating near term versus long term. Like the reason I'm pursuing this idea, is it because of something near term or is it because of something long term? And just really being honest with yourself of, I'm going to pursue this augmented reality sensor-based approach because in 10 years, I think that the technology is going to be able for me to deploy it. If you go in with that idea and you talk to clinicians and you say, this is an idea for 10 years from now, I think you'll get a different response than if you say, everyone's going to wear one of these in 6 months from now. This is not the right approach. And so just continuously evaluate what your idea is and where it's kind of the stopping point is how I try to cut bait.
Yeah, I mean, the way I think of it is we're sort of all on the same team. We all want kind of the best work to be done to impact people's lives and kind of make the world better. So I want that for my colleagues, and I think they want that for me. So I talk with people like, Levi and my colleagues in Michigan and others in the field, and we kind of talk about ideas and I get feedback, and that's kind of like part of how I try to understand what's worth pursuing and what isn't. And it's sort of that combined with like a pretty rigorous kind of rationale vetting process. So like, how do we know that this is worth doing? How are we convinced? There's a framework created by DARPA called the Heil-Meyer Catechism. And that's like a pretty good framework, I think, for looking deeply into like, is this idea valuable? So sometimes we use that as kind of a lens to look at a question. But like in general, I would say we do our best. And a lot of times we get negative feedback on grants and we, try to revise and make it better. And ultimately, like we're all shooting for technologies or research that makes people's lives better. And so that's kind of like keeps it going. And even when we get critical or negative feedback, maybe it doesn't hurt so much.
So I guess it could be summarized to critical evaluation of the idea and critical from the viewpoint that you try to be as rational as possible and objective as possible. And What I do is try to keep in mind that I will have a particular attachment to the idea because I had it. But that doesn't necessarily make it, better or worse. And what is true is that I think we all have been told that one of our good ideas was a bad idea by somebody who has in a better position of power at the time. I think we all have gone through that. That is like a common thing.
Yeah.
And I think at that point, for me, it was that the evaluation I did of the idea, it just withstand the criticism. I mean, the criticism didn't hold to what the reality I was observing with the idea.
Mm-hmm.
I think for me, that's happened twice, whereas the experts have been right like 8 times. You know what I mean? So I'd say that in general, the people who have a lot of experience who are trying to help you, it's different if you have your Facebook expert telling you something versus a close colleague that's trying to help you, or, the community of experts that's trying to help you. Generally speaking, I would say like 8 out of 10, 9 out of 10, that community is probably knows what they're talking about. So while you don't necessarily need to not do your idea, you should think about either conveying it better or modifying it slightly to some extent.
Yeah, I think I agree with that 100%. And I do some work with Google X, and one of their kind of values is to be like passionately dispassionate. And I think that kind of summarizes it really well. So you want to be passionate in your kind of investigations and de-risking and your rationale, but then you want to be dispassionate when you assess your idea and like, is this worth doing? Is this going to make the world better? Is this going to affect people's lives? Are we addressing a relevant question? So like, I sort of like think that summarizes it reasonably well.
Take the passion to power through and then use critical thinking and rationality to evaluate the merits of the idea. Excellent. So I think that's a good way to wrap up. Thanks a lot for participating in this. I was planning to be a bit of a short talk, but hey, it's a podcast. There's no cost on it, so we'll just let it run. But yeah, thanks a lot.
Can I add like one thing?
Sure.
I just want to point people to the Open Source Leg website, which is www.opensourceleg.com. On the website, it includes like detailed assembly instructions, solid model files, bill of material, vendor information, tutorials on control and sample code. There's open source data sets. So essentially everything that someone would need to kind of research and decide if they would like to either build the leg themselves or have us or someone like Humotech who is interested in building these legs for people. So if they're interested in kind of pursuing the open source leg, check out the website, opensourceleg.com, and you can reach out to either me or Levi, and we can help you learn more or get started.
Great, thanks. I'll put a link to the article and the project and to your personal webpage so people can reach out.
Sounds perfect.
Thanks a lot.
Thanks. I appreciate the opportunity to speak about the work. I think the podcast is a great idea.
Yeah, I thought this was awesome. So thanks a ton for the invitation.